So for today, we have a conference titled Mine Waste Management, Change Management or Management of Change. So mine waste facilities exemplify the adage that the only constant is change. These facilities are conceived, designed, constructed, and operated over years, if not decades, to become some of the largest engineering structures on Earth. Design bases, construction, operation, and decisions along the way change as these facilities are developed in response to many factors. The facilities are designed to be robust, resilient, and with sufficient redundancies to avoid catastrophic failures leading to the release of mine waste and water. While no engineer or owner has a crystal ball to see into the future, how is a safe facility brought into operation and developed over its lifetime and close? Such safe facility are requirements of society, financiers, owners, regulators, and engineers. Recent catastrophic dam failures have made this the non-negotiable reality of mine waste facilities. This presentation will speak to some of the considerations and approaches used to achieve safe mine waste facilities in recognition of the even present changing landscape. Purposefully developed using the pose many questions yet provide few answer style, the objectives of this presentation are to help you think outside the typical engineering box, foster discussion, and provide food for thought for some who enter the practice of mine waste management. So to address this discussion and give us those tools, today is with us engineer Paul Bedell. He is a geotechnical engineer working for WSP Canada through the acquisition of Golden Associates and is based on Vancouver in British Columbia. Paul has 27 years of experience working on mine waste facilities all over the world, ranging from equatorial to Arctic locations and having production rates ranging from a few tons to over 140,000 tons per day. His services range from resident engineering to design, operational support, permitting support, and engineer of record services. Paul is registered as a professional engineer in BC, Ontario, Saskatchewan, and North Territories. His current major assignment is to engineer of recording for Tech Quebrada Blanca to tailing management facility located in northern Chile at 4,400 meters over the sea level. That includes 120 meters high starter dam, developed into a 310 meters high sand dam at a processing rate of 140,000 tons per day. So please join me welcoming Paul.
Great, thank you, Daniel. I'll hopefully be able to successfully share my screen again. Daniel, could you confirm, please, that I have shared it correctly?
Yes, we are watching your screen. Thanks.
Great, thank you. Okay, so as introduced, I'll be speaking from a mine waste management perspective, which is my area of practice and has been my entire career. Titled Change Management, which you've probably heard of a lot, but the reality is how do you actually manage through change with that. My original working title was Lessons Learned from the Business End of a Baseball Bat, and that's really where I'm coming from, is the the various experiences that I've had that are outside the conventional engineering training that you're probably exposed to, certainly in your day-to-day schooling, and just some of the major things that you need to think about for projects. So a bit of an outline as to what we'll touch on today. I'm going to kick this off with a health and safety moment that's quite typical for those of us in the mining industry. Health and safety is critical to everything we do, especially as professionals. It also helps to frame the discussion for this today. Quickly touch base on who I am again with the introduction that Daniel gave. Then I'll move into some framing as to what mine waste facilities are, give you a quick primer and explain what the real business of mining is. Spoiler alert, it's not copper, gold, or diamonds. And then the constancy of change. That's a key requirement that we as engineers keep in mind and track over time, think forward, and always analyze as to what the change meant or didn't mean. And then how the influence of time impacts everything. And then we can go to a bit of a Q&A. So my health and safety moment, I'm sure a lot of you have seen this failure or heard of it. It was the proverbial straw that broke the camel's back in the mining industry in 2019 when the second failure of a major dam occurred at Bedell. It was in January of 2019. We've just passed the 4-year anniversary of that. It resulted in upwards of 252 deaths with that. So if this works, what I want to do is share with you the video that was captured of the dam failing. What you'll see here is static liquefaction of the structure in the background. And there are people on the dam. There's a major cafeteria downstream of the dam that these people are killed instantly on. The dam tow, as it's blowing out here, is moving in excess of 200 kilometers an hour just for speed. This is an instantaneous failure. This is the flow of the tailings much further downstream on the mine site, moving at about 60 to 70 kilometers an hour at this point. Think of toothpaste coming at you with this. You can see the equipment moving about, trying to get out of the way. A few of these operators were saved in that their vehicles were actually lifted and floated on these flows. But again, unfortunately, many people lost their lives. Far too many people lost their lives. So coming out of this was the development of the global standard for tailings management, which heavily influences our practice today, captures a lot of good practices, and sets the bar, frankly, for what the industry needs to deliver from a societal perspective with that. So why me? Like I said, I've spent my whole career, coming up on almost 30 years, in mine waste management. Started with Golder and then migrated to WSP. I've done everything from design to resident engineering, which is implementing and interpreting designs into construction. Permitting, operational support, working with the operators as to how these facilities are operated and developed over time, and then engineer of record services. The engineer of record is the individual who is accountable for auditing and confirming that the owner provides a safe facility, and also providing time-bound recommendations if corrections need to be affected by the owner with that. And as per the introduction, I've been very fortunate to work all over the world. I've worked with many gifted professionals who have guided my career. Those are some of the baseball bats that I've grown up at the business end of. How do we frame a mine waste facility, especially for people who aren't familiar with these facilities? They are some of the largest engineering structures on Earth, which is a real blessing in terms of experience. Very few engineers actually get to see fully implemented and operated, let alone closed, designs. Think about a bridge engineer. How many big bridges actually come to fruition that you can actually see over the course of your career? These facilities are happening all the time. And extend out lifetimes of tens of decades at times. That introduces a number of challenges that we'll speak to, in that, unlike a conventional water storage dam, think of the Hoover Dam. The Hoover Dam was built start to finish and then brought into operation. The dam doesn't change over time. Mine waste facilities, they typically will stage construction to match what the storage requirements are, and they link it in with the development of the mine itself. So these change and evolve over time, and a lot of challenges need to be mitigated in regard to that. They are incredibly multidisciplinary with all facets of this, from design through construction, operating, permitting, and closing of these facilities. You'll have metallurgical individuals, geotech, hydrological, hydrogeotechnical, mechanical, electrical, processing people. It's a really interesting set of team and skills that you need to pull together, and not one practice can do it on their own with that. As I started off with the health and safety share, that the catastrophic failure of dams and the release of tailings is the fundamental incident to avoid. This no longer acceptable in any way, shape, or form. It's now a firm requirement of society and financial institutions. Following Fejau, this is where the global standard was developed, and that was led primarily by the Church of England initially with their investors, and the principles for responsible investment in Europe. Those were the groups that got together and came back to the mining industry and said, we control the money. This is no longer acceptable. Figure it out now with that. So we now have the global standard on tailings management, and that is the fundamental requirement for the mining industry now. Insurance companies are now entering into the discussions of how these facilities are insured, what they need to understand, what they need to have in place for that as well. And the avoidance of catastrophic failure dams as they work towards designing, figuring out your design loads, and also the operational requirements. Those are long-standing requirements for Golders and now WSP's mine waste practice with us. So again, the global standard serves to strengthen what we had for a number of years, and now it's a non-negotiable with that. With regards to mine waste facilities, with all that said, there's a large risk profile that's ever changing and that ever needs to be managed, mitigated, and addressed with that. So some words of wisdom that I've glommed onto over the years. Fundamentally, tailings facilities typically have a very high consequence, namely catastrophic failure leads to loss of life or significantly unacceptable environmental impacts. And you want to have those managed with low likelihood of occurrence. From Mount Poly, I'm borrowing heavily from that report here, is that tailings dams are complex systems that have evolved over the years. They are also unforgiving systems in terms of the number of things that have to go right. Their reliability on consistent, flawless execution and planning, subsurface investigation and analysis and design, in construction quality, in operational diligence, in monitoring, in regulatory action, and risk management at every level. All of these activities are subject to human error. That's a key thing to pay attention to. Unfortunately, people are flawed by definition, and people have to be involved in these. I particularly like Mike Davies' words back from 2002, his axiom that tailing dam failures are a result of design, construction, or operational management flaws. They are not acts of God. They just don't happen out of the blue with that. So it's a daunting opportunity to get involved with these types of facilities, but highly rewarding. I can speak to that. I get up juiced every day to do what I do. Some of the things that you'll learn moving through mine waste facilities is that, like I said, you've got different ways of looking at it, different types of disciplines and whatnot. Some of the things that drive me nuts, operators, those who are turning on and off spigots, who are trying to raise the dam. Operators typically like to take the approach that everything needs to be easy. And while that's true, you need to have and bring into consideration that this work has to be executable in the field and feasible. there are things that are non-negotiable from a design, operation, and risk management perspective, and it's making sure that that is communicated clearly, explained, and understood by everybody. Mother Nature, she never reads the design criteria, and she's ever changing the design criteria with that. Never stays inside the playbook. Think of the extreme weather changes that we're getting now, climate change being a prime example of that. With all due respect to my geological colleagues on the right-hand side of the screen, I don't think I really need to say more about geologists and how things go with them. In fairness, as a pit is mined, for example, and we use those tailings that are sourced from the pit after processing, they rely on a model, but it's not until full operations get going, they move into the next phase, that we can actually understand and more fully understand and characterize the ore body and its behavior, which influences the behavior of the tailings. So again, we need to make those connections very strong right up front and understand what drivers we have and what we can control. Designs are typically constructed and brought into operation before tailings are ever produced by the tailings plant or the process plant. This is the big challenge I have at QB2 right now, is that our design is based on pilot plant tests. That's typical for a new operation coming online, but I won't breathe easy as the EOR until the process plant has actually fired tailings through it, and I can actually see what the grind of the tailings that the plant actually produces, how they behave, and we can more realistically characterize those to validate the design assumptions and then better understand what needs to happen moving forward. Mine plans and processing schedules change constantly. As soon as you start a design, typically with a tailings facility, you understand what the total tonnage will be produced over what lifetime, so you have a processing schedule. Of course, once you get going, the geologists have a tendency of always finding more ore, which means now we will have a fixed footprint, a fixed style of development, because we have to design the end point and then pull back to figure out how we stage that. How do we adjust that moving forward? How much flexibility can we bring in versus what needs to be a hard stake in the ground? As I said before, the ore body characterization, like any good geotechnical investigation, once you start digging a foundation, that's when you actually get to see better sample size, better behavior, better characterization. Same thing with the ore body as it's being exploited and brought to surface. Personnel and ownership changes. There is a real glut for human resourcing, even in the engineering world, especially with roles such as EORs, review boards. There's a finite number of us that can do that type of work well. And people in mines move about, they change. So there's a real need to bring in more people. But again, understanding that careers come and go, they start and end. How do you transition and bridge that gap of capturing the information, documenting it, and make sure it moves forward? That's a key challenge for any operation. So risk. I'm a big proponent of trying to steer a conversation away from risk, as risk is the outcome of a calculation, typically likelihood versus consequence. If you can talk about likelihood and consequence of a given hazard, then you can understand what you control, likelihood or consequence. And do those numbers change over time? That's a key one. I use this explanation when I try to explain to my mother that I'm safe when I'm either mountain biking or rock climbing. I try to reduce the likelihood of falling by getting better, but I limit my consequence. I stay on easy stuff where I'm very unlikely to fall. Also, I use all my safety gear and I climb with people who literally I trust my life with on that. A couple of reading recommendations. These are critical in my opinion. One is by Dr. Morgenstern in 2018. The 6th Victor de Mello lecture, I borrowed a lot from that in my thinking. This really codifies a lot of lessons that I'd learned over the years and helped put it into context even for me. It's an excellent paper, well worth studying and revisiting, frankly, a number of times, as is Peck's classic Rankin lecture paper on the advantages and disadvantages of the observational method. That's a must read for any geotech. And again, you keep coming back to it. Each time you read it, you'll get something new from it. So continuing on the path of how did we get to the state that we are today, and why is this a big driver? Tailings dams failures are unfortunately nothing new. They've been killing far too many people over far too period of time. I've just happened to grab three shots here, one from Stava in 1985, Marisput in 94, and Fundão in 2015. That was the first major failure in Brazil with that. So there's an unacceptable consequence to these failures. They've been happening far too frequently for far too long. Again, that's where the global standard has really inserted itself and is a watershed moment in the mining industry for this, with the objective for zero harm to people and zero harm to the environment. A recommendation that I would make, a good colleague of mine, Terry Eldridge, in 2019 in Vancouver's Tailings and Mine Waste, gave a keynote address called Lessons Yet to Be Learned. It's on YouTube. Make yourself a coffee, sit down for 40 minutes, and then watch it. And I guarantee you're going to want to watch it again. In that talk, Terry makes the point very clearly that we've known for far too long technically how to avoid such failures as these. We actually need to implement what we understand so that this doesn't happen. So for a primer on the mine waste management, most miners will tell you that they're in the business of copper or gold, whatever the resource happens to be, or recovery, how quickly or how much they recover from the ore. That's a question of rate and also income for them. Mine waste management is, in my opinion, the ante that you have to pay to play the game, because that's what they're really in the business of. It's intimately linked to the social license for the mine to operate, its safety. Frankly, it's a life and death situation where they have to assess this properly. Financing, insurance, the consequences of failure. Governance is an item that is gaining more and more traction in the mining world on this. Having a very sound and in place governance structure for a mine waste facility is fundamental. That's been purported for years by the Mining Association of Canada. ICMM is now on board with this, as is the global standard. The good governance requires good engineering, good operation, and good management. Bad governance enables and actually promotes bad engineering, bad operation, bad management. Reputation and corporate existence are other facets for this as to why the mines really need to pay attention to this. If you're aware of the failures in Brazil as examples, CEOs were fined and imprisoned for the failures of the dams. To the best of my knowledge, no CEO has ever been charged or jailed for not meeting their ore recovery or how much money they made for the company, just to put that into perspective. So mathematically, I can show you this with that as a case example here. Let's assume that we've got a diamond mine that has just under 2.5 million tons of ore processed, and they recover 2.2 million carats of diamonds every year. So how much good stuff? 2.2 million carats of diamonds equates to about 1.7 tons of diamonds. That's what they're after. That's what they want. How much waste do you have with that? So they have to process 2.480 tons less the diamonds that they recover from that, and they end up with just under 2.5 million tons of waste to manage. So you tell me, what's the business of the mines in, diamonds or waste management? And of course, the answer is mine waste management. Almost 100% of what the mine touches is waste. They have to do it safely, they have to do it efficiently, and they need to do it mindfully in order to get it right. And I've, over the course of my career, as I get more gray hair, when I'm working with a client to help frame them, to understand the importance of this, I'll actually put this math on the board to show them where I'm coming from with this. So the constancy of change and perspective with this, there's different ways to look at the same item. So as an example, client wants a swing on a tree, obviously padded and very comfortable, and you'll notice the price tag of $0. Thankfully, we don't have to deal with a lot of architects in mine waste, but architects look at the world one way. The design is always different than what the client expectation was. Enter budgeting in terms of what the engineering budget was, what the client's budget was, and some different views on that. Liability insurance, it's a bit of a sick joke with the Hangsman news there. Estimators and into it. Sometimes we need manufacturers to input into the design and construction. Inspectors, contractors, including the mine if it's a self-perform piece. And then there's really what the client wanted. They just wanted a simple swing versus what was described. So again, expectation management and clarity is critical for this. How the project was documented. This is the space that I typically live in as a consultant, and certainly as an EOR with that. And documentation is critical because that's your number one control, critical control for personnel change. Because if somebody leaves the project, typically that institutional knowledge is stored in their head. You need to get that knowledge out of their head and onto a piece of paper so that it can be shared and understood by other people. It's super critical. We'll come back to that topic in particular. And as you work through this whole process, of course, the customer's bill goes way up with that. So the constancy of change. This was a facility that I worked on a number of years ago. We were working on a diamond mine. The terminology for their waste is processed kimberlite. So the design and the plan initially with the mine was that half of the waste would be placed back underground as backfill. What was placed on surface would be paste as well. So they wouldn't have to split the streams. So 50% underground, 50% to surface. The design was exploited that we could progressively close as the facility was advancing, and that's critical rather than run the facility through the end of mine life. In this case, it was 40 years, and then start to close. If you can get progressive closure in real time, does a couple of things for you. First of all, it gives you, if you can start closing a facility in the first year or two of a 40-year operation, then you've got 38 years worth of experience on the first piece that you've closed, rather than run it through to 40 years, then start closing, and then hope for the best. You can learn from that. In some jurisdictions, closure bonding, you have to pay up front until you start closing the facility. The idea being there is that the mining company can't disappear, and then the government is left holding the bag to pay for closure. So they bond it up front. If you can progressively close and demonstrate closure, there are mechanisms whereby you can get that bonding back earlier. That's the financial carrot for the mine to do this. And we had a lot of water management designed into this facility as well. All of these changed once we started operations. Some of them were removed altogether. again, during operation. I liken this to trying to operate on a live patient, because we had to change the design, the construction method and requirements, and the operational procedures as we were filling the facility. The plant had already been turned on, and turning the plant off was infeasible for the project. So it was a stressful period, to say the least, as my team and I worked through this with the client. So, it's what does the patient want, or what is the patient expected to do, and also to be kept alive at the same time. And that also depended upon who you spoke to, be it the mine team, the processing team, the guys doing the mine waste facility. All of them had a different perspective on things. So it was an interesting challenge, to say the least. So I've got a quotation here that I stumbled across a few years ago, and I thought it was quite good, as it touches on a number of points that I've just been speaking about. So I've got a couple of slides that I'll read to you here. So there are two approaches to a natural problem. They are the approach of the pure scientist and that of the engineer. And again, as a reminder, engineers apply science. We're not scientists. We're trained in science, but we apply science as engineers. So the pure scientist is interested in only the truth. For them, there is only one answer, the right one, no matter how long it takes to get it. For the engineer, on the other hand, there are many possible answers, all of which are compromises between truth and time. For the engineer must have an answer now. Their answer must be sufficient for a given purpose, even if not true. For this reason, an engineer must make assumptions. Assumptions in which case they know not to be strictly correct, but which will enable them to arrive at an answer which is sufficiently true for the immediate purpose. Mistakes are not made when an engineer makes their assumptions. Mistakes are made when other engineers forget the assumptions which have been made, and assumptions on which a theory is based are too easily forgotten. This was from Hugh Golder back in 1948 in a paper that I cited the reference there. So that speaks to the importance of documentation, communication, and also revisiting the design assumptions versus validation during operation. The fit for purpose at a given time. If the design objective or if the major influences for a facility change over time, you need to go back and understand what that means. If you think back to the dam that we watched fail in the health and safety slide with that, several elements of the design changed over time. And the question would be, were they mindfully done in consideration of what was built before, how it was operated, future operations? So this is super critical. There's some really good guidance and reminders in this piece from Golder. So how time enters into this. I've borrowed this concept and taken it a bit further from a presentation I saw with Steve Vick a number of years ago. He called it the engineer's method to get through accounting hell. You'll see what I mean in a moment. On the horizontal axis, we have time increasing to the right. On the left axis, we see the cost of money in blue. And on the right-hand side, the red axis is the likelihood of failure. So the cost of money, the blue axis on the left, that's the accounting view of the world. Likelihood of failure in red, that's the engineer's view of the world. So what we're looking at here is over time, the cost of money typically goes down. This is conventional accounting wisdom that we want to spend later. We want to defer cost. The engineers, on the other hand, look at the longer time of exposure we have to something, the likelihood of failure goes up. There will be a larger rain event. There will be a larger earthquake as examples that hit. So how do we balance these two things? There's a bit of a sweet spot in here in that, you don't want to spend all your money up front if you can rationalize why pushing it off to some point makes a little bit more sense. So an example would be The day that your first child is born, you certainly want to start setting up a university fund, but you're not going to throw all the money down on day one. And you probably don't want to pay for it just as they're enrolling. You'll invest that over time when and as it makes sense. The same thing for engineers. We can't always design everything out. Some things are infeasible to do that, but we can manage them appropriately over time. And we try to identify what this sweet spot is in order to do that. Adding to this concept, we have vulnerabilities in terms of the changing over time of what an adverse loading condition could be. Climate change is the immediate example that pops to mind on this, in that we're starting to see more extreme weathers over time and norms. And the recommended practice now is not to revert to a historic based storm event, which was used when I started my career in Northern Ontario. We would always point to something called the Timmins storm, equivalent to a PMP type of event. We're trying to be a little bit smarter over time with that. And we can look at how can we, first of all, identify the band, and then is there a way to narrow that up in the design and construction so that we can become more resilient with that. Also, the cost of money isn't a single line. There's also a band in there too that's termed coping cost with that. So it's a bit of a paradigm shift to start having these conversations with this. You'll see if you look at the Mining Association of Canada's climate guide that came out a couple of years ago. This style of diagram is in there. That was something that I pushed pretty hard for to try to get that in when we were pulling that together with Mac. So it has gained some traction in this thinking, rather than the typical historic practice of pointing to a specific storm and then trying to meet or exceed that in the design. So some of the things that we want to just capture and start thinking forward is closure is obviously a huge component to a tailings facility. As I said before, progressive closure is something that I think we've got a long way to go on with that. We always talk about designing for closure. I think that's gained some traction, certainly over the course of my career. That's much better defined, much better executed. I think the next paradigm shift will be operating to closure. How do we actually get the operators to understand that the closure plan is something that they need to try to operate to, rather than the past and historical way of looking at things that, well, we'll just close it when we're done. You can do some things during operation there's synergies to be gained there. Permitting and closure are intimately linked in just about every jurisdiction that I've worked in. So again, that is a big carrot that has to be hit now for the mining companies. And like I said, operations is, I think, the missing link right now with that. Design modifications, these, as I said, change all the time. Capital expenditure and operating expenditure certainly come into this. The code word for that is when a client says we want to optimize the design. Optimize just means they want to get the price down. And again, you can work with the client on that, but there are some elements in a design that are non-negotiable. Those need to be made very clear to the client with the risks if they're not achieved, and certainly what the risks are likely to be if they don't listen to you as an engineer. Again, that's a lot of conversations that need to be captured and understood with that. Regulatory and permitting. Once a design goes into about feasibility level, that's when the regulators and the permitting teams really start to pay attention to a project, and a lot of commitments and requirements are made at the feasibility level that will impact when you move into detailed design and certainly in operations. And some of these cannot be moved away from. So those, again, need to be captured and understood and thought through mindfully. Construction. As soon as you open the ground, that's your last phase of planned investigation. You know, you can do a really good geotechnical investigation. I remember John Sachuk telling me a long time ago that the very best geotechnical investigation for a high-rise building, you will see 1/1,000,000th of the site, and you have to base your design to have millimeters worth of settlement. And his question was, so is geotechnical engineering an art or a science if you're doing that? Once you open up the ground, you can actually see it. You can characterize it much better. You can assess its behavior. So what are the actual conditions encountered in the field? And you need to think about that in the design. You know, we're always bounding things as geotechnical engineers. We're taking incredibly complex systems, natural systems, and then trying to simplify them such that we can understand them, characterize them, and do a design. But what if the conditions in the field are outside of what we made allowances for or assumptions for in the design modification? So again, that goes back to Golder's words. You have to remember what the assumptions were. What were the limitations made, and why are they not important, and how do you validate them with that? Again, optimization. Everybody wants to lower the price, especially when you're getting close to the end of initial construction and you're just about ready to turn the plant on. That's when everybody wants to tighten the purse strings, and they want to try to get done and across the finish line quickly and cheaply. And again, some things are non-negotiable. You need to be clear on those. During operations, alignment with the design intent is critical. This is basically where an engineer of records lives, with constantly assessing what was done, what is being done, what will be done. Does that align and satisfy design intent? That's the piece that, you know, super exciting, super stressful. I won't kid you. It's an interesting place. Operators too want to lower costs and optimize. Ore body understanding, decades-long periods of operation in terms of state of practice, evolution of the ore body, personnel rotation. I'm working on a site where we recently experienced an individual from the client side who retired after working on the site for 26 years. Now, Greg did give us enough time to understand that, but when he did say, I'm retiring in a couple of years, everybody panicked, because then they started to figure out they needed to get every piece of information out of his head with that. There's financial constraints, there's technology changes, and societal changes and pressures. Again, the global standard was born from society, saying enough is enough with these facilities. So again, with closure, as we're designing, we typically try to define what and how to close a facility. Those are key bases for closure. And then we keep modifying them as they're ever changing during the operation. I liken this to trying to hit a moving target while you're on a ship in a storm. Not that easy to do. Again, really, really interesting and fascinating part of the job, but it does get stressful at times with that. So that's what I've been able to put together to try to summarize some of the things that you may not think of, especially those of you who are finishing up at school, where typically the assignment is relatively well defined by your profs. You've got your question, you know how to run the engineering, and you get the answer. Things change in the real world where all of those pieces change along the way, and you're trying to navigate that with your clients, with your teams, and with yourself. So lots of food for thought. I can take questions now, Daniel, if there are any.
Okay, thank you, Paul, for the very interesting conference and those perspectives. So now we are going to begin the question sessions. So we have 2 questions online, right? Or 1? Okay, 1 question online, but we can also begin with questions here in the public. Anyone has any question? Okay, let's begin with the one online. Give me a moment. I'm moving through. Okay, so the question comes with a comment, said, "How, Paul, thanks for this interesting presentation. Considering climate change knowledge to be documented to comply with GISTM, is a climate change resilience assessment must be done for an extreme TSF for which a return period of 1,000 years will be considered for, does it say? I don't see. A storm and seismic design? Thanks.
I would say, yeah, you're going to have to consider climate change as a matter of practice now. Again, I mentioned the Mining Association of Canada's climate guide, which is the best one I've seen, the only one I've seen for that. The extreme TSFs, yeah, I think you're going to want to look at that anyway, just to understand what the loading conditions are. Extreme loadings are typically the starting point for any facility. Certainly the global standard advocates for that. We here have been advocating that for a number of years, to step back and reduce your design loadings. What does that mean? What it means is you're knowingly accepting that if a larger event happens, you don't have the ability to convey the flows and manage them properly. You don't have the resilience to handle a large earthquake event. What does that mean? It means you're accepting a greater likelihood of failure. So that's why we want to start with the extreme loadings. And what does that actually mean? You know, in a location like Canada, for example, we're not super high seismicity, so it probably means flatter slopes. We don't get a tremendous amount of rain relative to the rest of the world, so it probably means a slightly larger spillway. As a geotech, I'm always going to make my spillway bigger than what my hydrologist tells me, just because I want extra flow capacity with that. So I think the climate change piece definitely needs to be looked into that for defining what those events are, especially the precipitation related ones.
Okay, thank you, Paul. Any question here? Okay, we have a question.
Paul, can you hear me?
Yes.
Hey, Paul. Just one question on your slide 16 there, where you shared a quote with assumptions. Have you ever worked on a project where you've come in a facility that's already been operating for some time and found that there is no DBM, you're not satisfied with the DBM, or that you're seeing that the assumptions that were originally made aren't being interpreted properly? And how did you handle that?
Yeah, great question. The short answer is yes. We run into that a lot. The climate change question does that even with quote unquote an acceptable design that was done in the past. And also, if you've worked with seismic teams, they seem to want to increase the seismic loading evaluation every 3 to 5 years with additional information and additional guidance provided to them. So revisiting what the design bases were is an iterative process, even for a new facility. You've got to have that cued in to your workflow. Being on a site, yeah, I'm EOR for an older facility that's about 60 years old. Not surprisingly, when we first got involved in that 60 years ago, the attention to documentation was nowhere near what you would expect and require in today's age. So we've had to, that site is, I say that site is experience rich, documentation poor. And we've tried to backstop that. When we do identify on other sites, items that don't jive with what we would expect, or if we think that the loading condition, as an example, needs to change and be updated, that's when you have to assess what you're looking at. What does that mean for the stability and performance of the structure with that? And that enters into an interesting discussion in stability. For example, if you say, okay, 1.5, factor of safety is 1.5. If your factor of safety that's calculated is 1.4, is it a stability issue or is it a compliance issue? Compliance is 1.4 does not meet 1.5. But 1.4, is that far enough away comfortably from failure, which would be unity with that? So you can enter into those discussions, but reassessing and evaluating changes over time is critical. You've got to be clear on what the risks are or could be for situations like that. And again, that's a big piece of why we want a design basis report, the DBM, that the global standard specifically calls for now, pulling that together and understanding what it means and what the risks are. It boils down to a risk-based discussion for what does it actually mean, and is how, if anything, needs to be done.
Okay, thanks, Paul. Next question is, will the application of GISTM by mining companies result in zero catastrophic failures in the future? Thanks for your perspectives.
Yeah, well, that is the stated objective of the global standard. And there's a lot of excellent guidance provided in that. As I spoke to, the governance piece is fundamental to that, and understanding that. It's also starting off by the application of extreme loadings is also alignment with all of that. So yeah, that is the stated objective of the global standard. And for those of us that study that standard, live under it, and work with it and promote it, yeah, I've got very high hopes that will be achieved once the standard is universally adopted and applied.
Is there any question? We have a question.
Hi, thank you for the presentation. I'm curious to know how you manage being engineer of record on sites where you're working remotely. You don't have your feet on the ground. How often you would be visiting, and how you manage when things go wrong and there's short response times.
Sorry, I caught the first half of that, but not the specifics in the second half. Could you repeat it, please?
Before I cut out, curious to know how you manage reacting when things go wrong, when you've got short timelines to make a decision, when you don't have your feet on the ground, and if that does happen often.
Okay, yeah. Well, one of the key mitigations for that is again to think through what might happen, and if something does happen, what can you do? That's the observational approach, and plan for it. There are some things that if it happens, there's nothing you can do about it. If you think about the Teton Dam that failed in Idaho a number of years ago, where the result that resulted from piping failure. Once piping starts, there's nothing you can do. Just get out of the way with that. So for piping, the critical control for that is a proper design and proper construction. Obviously, you've got boots on ground for that kind of stuff. In terms of other controls and how you manage it, as the EOR, I want a team on site, certainly during the any initial construction. Again, that validates and gives us a better understanding what the actual geotechnical conditions are, especially if we're excavating key trenches or removing foundation materials with that. As EOR, I will be on site a lot for that myself. Moving through in operations, again, startup of critical activities and monitoring. I'll either have a team on site or I'll be on site for that. There'll be certain placeholders for items. The classic is if a site experiences precipitation event of so many millimeters or more, I'm on site instantly. Monitoring data is given to me all the time. Same thing with an earthquake. If a large earthquake hits, I'm instantly on site to look at something if we don't have boots on ground. So it's partially getting out ahead of it and defining at what thresholds you need information, including when, as the EOR, you need to be on site. The idea is that you've got a staged response plan to understand where your thresholds are, so that you don't get a nasty surprise. You can curb it and control it before it becomes an emergency.
Okay, our next question is also about GISTEM. Says, is it possible of achieving the zero catastrophic failure, but GISTEM application on legacy structure?
Yeah, that's a really good question. I would have to say, if it was a yes/no response that's expected, I would say yes. It's possible. It certainly needs, legacy sites, older sites. They're tough. A lot of legacy sites, like the one I talked about, that's 60 years old, not a lot of initial as-built information, not a lot of pre-development conditions, not a lot of geotechnical investigations relative to what we would expect in today's practice. So with legacy sites, there's often a need for the EOR to critically evaluate the situation, say, do we actually understand this site well enough? If not, what do we need to do to mitigate and bolster that understanding? Additional investigations of the deposit, of the dam, of the foundations, what's feasible, what isn't, how do you mitigate that? So yeah, all of that feeds into the zero catastrophic failure objective for even the legacy sites.
Okay, so thank you very much, Paul, for joining us today and being here, sharing your knowledge on these perspectives. And yeah, we hope to see you all again next week with a conference titled "It's what you learn after you know it all that counts." So see you next week, and thank you.